Hello, this is Dean Waldo from Pacific Lutheran University with a short presentation on figures of merit. This is based on Skoog et al. And often used in instrumental analysis. First, let's just look at the figures of merit that we're going to be talking about. There's precision, bias, sensitivity, detection limit, dynamic range, and last, selectivity. Won't talk much about the last one, but we'll go back to the beginning here. And what I've done is I've created some data to work with, and we'll be able to talk a little bit about the various figures of merit. So if we switch to Igorpro, here I have in the first three columns concentration data, absorbance data, and the standard deviation of the respective absorbance data. Concentration ranges from 0 to 10 millimolar. And in terms of precision, we're going to think of that as the standard deviation of the measurement we've made. So in the lab, a student has probably measured absorbance multiple times and then calculated the average and standard deviation. And those are the values we are reporting. So to start thinking about figures of merit for this particular instrument and the calibration curve we're making, we need to plot that data and get the best fit to that. So what I will do is make a new graph, and I'm going to plot absorbance versus concentration. And you can see there's some variation in the data. Let's clean this up a little bit. I'm going to make markers. And I'm actually going to add error bars, which are going to be the standard deviation. So I'm going to say plus and minus the standard deviation of absorbance. And let's plot those data and enlarge that a little bit. I'm going to play with the axes a little bit to make that graph a little bit more user-friendly, shall we say. So I'm going to turn on mirror. I'm going to turn off I'll leave the standoff on for now. I'm going to use minor ticks, and I'm going to put the ticks on the inside. I'm going to give a little bit of extra room around the data points, so I'm going to go to the axis range on the left. Well, just all of them, and let's just set that to auto scale. Whoops, set that data limits to nice plus inset. And then I'm going to make both of those end up at 0, but space it farther on the high side of the graph. And then let's give this a label on the left axis. We'll just call this absorbance. Just say absorbance. And then in terms of absorbance units, bottom, we'll call this concentration in molarity. Okay. To keep thinking about figures of merit, we need a fit to this data, and as you can see up at the upper area, it's starting to bend over. This could come from a number of reasons. Most often it has to do with nonlinear detection response for a typical instrument. So what I'm going to do is use cursors, and I'm going to fit from 0 maybe up to here under data analysis curve fitting. I'm going to fit to a line. I'm going to choose absorbance versus concentration. I'm going to use cursors, and I'm actually going to weight this. Since I have standard deviations, I'm going to weight it by the standard deviation. And then I'm going to plot the full range. And then it rescaled things a little bit. I'd like to move this back down. I'm just going to click on the axis here so we get a better view. We're going to set that back to 2.5. And I'm going to move this up here. So at this point it looks like we have a calibration curve, and you can see the data fits really nicely within all the error bars, and then these 3 points are veering off that fit line, and it's outside the error bars. So we're going to consider this to be not effective for the calibration. I'm also going to only go up to about, maybe 12. There. So we have a bit better view of the data. So now we can start talking about figures of merit. So if we switch back to our information here, we've already talked about precision. Sometimes I will use a 95% confidence interval, often a standard deviation, and you can go back and remind yourselves about what a 95% confidence value is. And typically in my teaching, I use a student t-value of 0.95 for given degrees of freedom related to the number of measurements divided by the square root of the number of measurements. But getting to the more newer, shall we say, parts of the figures of merit that you're maybe not used to, bias, we're going to consider the difference between a measured average and the true value. So in our data here, the measured value is going to be whatever our calibration line goes to as the 0 point, or it could actually be the value we measured as 0. So 0.5057, the fit gives us 0.04 plus or minus 0.03. So very close to each other. And in many cases, you could use either one as your measured average. But then the bias is going to be the difference between those. And so we know the concentration at 0 should give us an absorbance of 0. So we have a bias that's positive by 0.049, or depending on which version you choose, 0.057. Now note the standard deviation is 0.05. So I'm going to go with the intercept of the calibration curve fit. Now in terms of the next figure of merit, that's going to be sensitivity. And sensitivity is defined as the slope of your calibration curve. And this is what we call the calibration sensitivity. And for our data here, the calibration sensitivity is 198.9 or 199. Note that the uncertainty in this slope is about 7. So we might report this as 197 plus or minus 7 in terms of slope, or the calibration sensitivity. Note that that tells you for a given change in concentration, what is the change in your signal. Now, that doesn't depend on how well we think we know our measurement. And so another tool that's been developed is analytical sensitivity. And in analytical sensitivity, you take your calibration sensitivity and divide it by the standard deviation of a specific point. So that's a specific measurement. So in other words, for our data here, we could then have an analytical sensitivity for each data point. So if we go to the table, I've created a wave, AS, for analytical sensitivity. So that's going to be essentially the slope divided by that second wave. So if I bring up the place that I can enter data, so I'm going to say A underscore S is going to equal the slope, which we've just done that fit, and so that's going to be the parameter of interest. And here is going to be W underscore coefficient bracket 1 bracket. So that's W underscore coefficient bracket 1 bracket, which just means it's the second data point in that data set. And I'm going to divide it by the absorbance underscore SD. And so that column that gets populated above, these are all of the calibration sensitivities for each of those points. You can see they vary as a function of concentration. We could even make a new quick plot here and plot our analytical sensitivity versus concentration. Just to give you an idea, let's just convert this to 0. Whoops. Convert the bottom of that scale to 0 just so we can see that a little bit better, and we can make this about 7,000. So you can see the sensitivity is getting a little larger as we go up due to the differences in the standard deviations. So I'll move that off to the side for now. So hopefully that gives you an idea of the difference between calibration and analytical sensitivity. Let's go back and now talk about detection limit. So in detection limit, that really is going to that is really going to designate what is the least concentration that can be distinguished from nothing. So in this case, we're going to take the average of the blank measurement plus 3 times the standard deviation of the blank and call that our detection minimum or detection limit in the units of the y-axis. We could put that in units of concentration. I'll call that C min, which is going to be your signal minimum minus the average of the blank divided by your calibration sensitivity or your slope. This turns out simply to be 3 times the standard deviation of your blank divided by the slope. And so in our case, let's go back and look at the data here. So the standard deviation of the blank is going to be 0.0309. So we'll take 3 times that divided by the slope. So if we go back up, we can just say, well, I'm going to say print and just get that value displayed in the history. So I'm going to print 3 times W underscore coefficient bracket. Now we need the first fit value, and actually we want the uncertainty or the standard deviation, so that's actually sigma, not coefficient. And we want that for the first variable, which is our intercept. So in the Igor parlance, it'll be W underscore sigma slash W underscore coefficient bracket 1 bracket. So we're taking 3 times the standard deviation of the blank divided by the slope. So this would be our detection limit, 0.00465. Various amounts of sig figs can be considered, but I'm going to put that here as our detection limit as the C min, concentration minimum. And I'm going to repeat that twice, and I'm going to give another column or set of data that's going to be in absorbance units, just so we can maybe add this to on the plot and get a better visualization. So I'm going to plot it from 0 to point, say 0.02. So I'm going to say 0 and 0.02. So now what I can do is I can add a plot of this on the graph, and it'll be a vertical line. So if I do append, and I'll go back to my concentration detection limit as a function of signal detection limit, and I'll plot that. Oh, and then I plotted it backwards, of course. So I need to remove that and try again. So I actually want signal detection limit versus concentration detection limit. And that was a little small. I actually want it 0.2. So here is our detection limit. Let's give that a different color. Now where that crosses the calibration curve, if we go over to the signal, that is going to be the signal minimum. And so if we wanted to figure out what that was, we could say print, and that would be the blank, which is going to be W underscore coefficient from our fit, 0 plus 3 times W underscore sigma bracket 1 bracket bracket 0 bracket. So 0.142, and if we go over here, we can see that makes sense, 0.142. But I often think it's easier to visualize in units of concentration, hence the vertical line. Okay. One other thing we can do is we could put maybe a tag on that or an annotation. Let's go to add annotation. And we could say C min, but I might want the min subscript. So if I do that and say start, notice there's the annotation for C min, but what if we could actually point to it so we had a better idea? So we can actually go to position and symbols. We can go to tag, there we go. And we're going to tag this. We're going to connect to the wave with an arrow. And the position is going to be on the signal here at 0.1. And, whoops. So you might find those kind of annotations helpful just to know about. So that's detection limit, both the signal minimum and the concentration minimum. Now for dynamic range. And dynamic range is composed of two major pieces. The first is what's called the limit of quantitation, LOQ, and that is the same average of the blank plus now somewhere between 6 and 10 times the standard deviation of the blank. Skoog et al. Recommends using 10, and if you go look in the analytical chemistry literature, you'll see people arguing from anywhere from 6 to 10 times that standard deviation. I tend to like 6 because 10 just seems so far away from and outside the possible values that you could measure of a blank. So I will use 6 in my example here. So in terms of the signal level, the limit of quantitation, that's going to be the blank average plus 6 times the standard deviation. And if you want to put it in terms of concentration units, that's going to be 6 times the standard deviation divided by the slope. So let's go back and calculate that. So I'm just going to go back up here to where I had printed the concentration minimum for the detection limit. Now the only thing that really changes is we're going to go 6 times that, or 2 times the detection limit, and that's 0.0009. If we wanted to see what Skoog's value would be, let's go to 10 times that. And you can see the difference there. It's almost another factor of 2, but I'm going to go with this value. And let's put it in the limit of quantitation position. So I'm going to put that in the second position. So I'm going to go from, or actually in both, and then I will use the S underscore as the signal wave. And if we go back here, I'm going to make it go up to 0.3 or so, just to see what that looks like. 0 to 0.3. Oops. Why is that? There we go. 0.3. Now let's add that wave. And that's going to be the limit of quantitation, S LOQ versus C LOQ. And here is that data set. And I'm going to again switch that to blue. And I might make that go a little bit higher so it's easier to be seen. So I'm going to go to 0.35. And I'm going to just go to here and duplicate that tag. and move this over here. I'm going to switch this to the other wave, and I'm going to change its name to LOQ so we can keep track of it. So you can see that gives you a pretty good idea how far apart these two are. Now, and let's go back over here. Now, if we think in terms of limit of linearity, that's going to be how high in the calibration curve we can go till it really starts to deviate noticeably from the calibration curve. Skoog says about 5%. If we start looking over here, about all we can say is that the point that's at 8 millimolar is definitely off the line. And so we don't know where between these 2 points the break would occur, so we will just assume that the limit of linearity is going to go to the last point we can measure. And so that point is going to be that concentration, which is the fourth one in, which is 7 millimolar. So I'm going to go here and say 0.007, 0.007. And at this point, I'm going to want it to go maybe to 1.6 or so for absorbance units. So let's go ahead and add that point. Graph append. So there's the signal, limit of linearity, and the concentration. So there is our line that sort of denotes that. And there. So let's take and duplicate this one again. So we'll duplicate that tag, and we're going to switch and call this LOL. And this is going to be now on the LOL data set, and we'll say do it. And so here is that. So dynamic range, that's the category we're talking about, really is between the limit of quantitation, there we go, and the limit of linearity. So we can actually draw that in conveniently with the drawing tool, Command T or Control T, and we can take and do that, and we can actually even put an arrow at both start and stop. And if we want, we can then put a little tag here. We can call that dynamic range. So there, we've gone over all the major figures of merit except selectivity. And in this example, I didn't include data on selectivity. But just to review what that is, it just says if you have a species, one species that can contribute to a signal, then you don't have to worry about selectivity because that's the only thing. But suppose 3 different chemical species may contribute in different amounts to the same signal you're measuring. So in UV-Vis spectroscopy, this could be 3 different molar absorptivities, but each of those calibration sensitivities are what you use to think about in terms of selectivity. So if A is what we're interested in, the selectivity of A with respect to B is going to be the relative ratio of those two slopes, B over A, or with respect to C, it'll be C over A. And if you're interested in A, you'd like Ka or Kb and Kc to be as small as possible. But they could be any value, relatively speaking, depending on what you're really looking at. But you really want the slope or calibration sensitivity of what you want to be much greater than what you don't want. Anyway, this hopefully gives you a very detailed look into figures of merit and how you can display those and think about those in the program called Igorpro. Thank you for your attention or patience, and that will be all for now. Hopefully you find this useful.